Yesterday we talked about the structure of the atom, and we said that inside the nucleus, which is that thing in the middle, right? Nucleus means middle. Inside the nucleus we have protons and we have neutrons. And those protons were positively charged. They're repelled, they repel each other by an electric force, but that's not the force that we want to talk about here. We want to talk about the force that attracts protons together, and the force, for that matter, that attracts neutrons together as well. We call it the strong nuclear force. The strong nuclear force keeps that nucleus together, attracts the protons to keep the nucleus together. Now, you also have another attractive force in the atom as well. It's called the electric force. Sometimes we call it the electrostatic force. That acts between these electrons that are orbiting around the nucleus and the nucleus itself. The nucleus is positive because of those protons. The electrons that orbit around it are negative. Positive and negative attract each other electrically. So there is this electric force of attraction that keeps the electrons orbiting around. These electrons, again, are attracted to the protons in the nucleus. But when we pump energy into this by a battery or by rubbing it or whatever, then sometimes we can overcome a force. But if we're going to overcome a force, we're going to overcome that electric force, not that strong nuclear force. And that's why when you rub a balloon against your hair, it's electrons that move as opposed to protons that move. It is conceivable to have protons move. That's a nuclear reaction. Sometimes we talked about that electric force being a repulsive force in the nucleus. Sometimes that repulsive force in the nucleus is so big because of the number of protons in there that it actually beats the strong nuclear attractive force. Then the nucleus is unstable and we get radioactivity, some kind of nuclear reaction radioactivity. But that's not what we're talking about here. Okay, we're talking about normal circumstances, normal means of supplying energy and so on, overcoming those forces of attraction between the electron in the nucleus and having the electrons go somewhere or do something, right? That's electricity, or there could be a chemical thing in there as well with the electrons doing a thing versus something happening to the protons in the nucleus, which would be nuclear physics as opposed to chemistry or electricity. We talked about positive charge, having more protons than electrons, and we learned that positive charge comes from not absorbing or receiving protons. You don't become more positive by gaining protons. You become more positive by, you're losing electrons. And you get negative charge not by losing protons, but you get negative charge by gaining electrons, right? It's the electrons that do their thing here. And neutral, of course, neutral is neutral. Equal number of positives and negatives. You don't need to gain or lose electrons in that case. The unit of charge we said is the coulomb. Is that a big unit or a small unit? Yeah, it's a pretty big unit. Do you guys remember the symbol for charge? So yeah, it's Q, little q. So we would say the charge of something is equal to blank coulombs, however many coulombs it is. And usually that's a fairly small number. Sometimes it's 10 to the minus 6. If it's 10 to the minus 6, we might see it written not as coulombs, but as microcoulombs, which if we do, we have to convert it to coulombs by multiplying it by 10 to the minus 6. We might see it as nanocoulombs. You guys remember what that one is? 10 to the minus 9. You don't need to memorize that because it's on your data sheet. What about millicoulombs? MC, yeah. 10 to the minus 3. I mean, theoretically, you could see any prefix in front of it, right? Even one that you don't recognize. I don't think I've ever seen centicoulombs, but you could, right? It's conceivable. All you do is look at your data sheet if you're not familiar with the conversion factor and figure it out, right? The middle of your data sheet, it tells you what all those conversions are. Always just remember that when you're doing a calculation, you got to be in coulombs. Charge of an electron on our data sheet. So if we look over here, it says it's minus 1e. Proton is plus 1e. So we're going to say minus 1e plus 1e. But that doesn't really help us a whole lot, other than to tell us the charge is the same, equal and opposite. What's an e? I don't remember. Let's check our data sheet. What is it? Yeah. Yeah, it's this elementary charge thing over here, 1.60 times 10 to the minus 19 coulombs. So we're going to say this is minus 1 times 1.6 times 10 to the minus 19, which gives us minus 1.6 times 10 to the minus 19. Whereas this one is plus 1 times the elementary charge, which gives us plus 1.60 times 10 to the minus 19 coulombs. Good? You guys ever had one of those tests where you're allowed to take in a cheat sheet or open book where you can take in your books? I remember a course that I had, Physics 215 at university, Digital Electronics, great course, loved it. It's kind of hard, but it was fun. We built things like circuits, like digital circuits. Our final project was to build a video card for a computer from scratch, just with logic, with the logic gates. It was great. It was really hard, actually, that project was, but it was fun because we saw something at the end of it. Our exams in that course, I remember, were all open book. We could bring in whatever we wanted, our notes, our textbook, and whatever other book we could find in the library that would help, whatever. So the first test, I remember everybody's like coming in like super extra prepared with all these extra books. It's like, okay, whatever question we're going to get, like we're going to find out how to do this from the book. And what happens? Yeah, if you don't know where to find something, like it's almost useless to have it, right? Like you get all these books, but it's like, well, where am I going to find the answer to this question out of all these books, right? Same deal here, right? Like if you're not familiar with the data sheet, we can say that the charge of an electron is on your data sheet, but it's kind of in a roundabout way, right? If you're not familiar with where to find it or how to find it, then you're going to spend way too much time trying to figure that out, even though it's given to you. So just be familiar with it. You don't need to memorize it, just be familiar with it, okay? Which would have helped a lot in that course if I was completely familiar with all those books that I brought in, okay? We talked about our ion notation here, okay, where we got charges on these atoms, which makes them not atoms, makes them ions, Al plus 3, O2 minus. This one just meant that we had a charge of what? 2? To what? To what, David? To what? Yeah, 2 times the elementary charge. Actually, negative 2e, right? So it would be negative 3.20 times 10 to the minus 19 coulombs. Okay, we used this analogy yesterday, right? When you're playing a song, if you're a musician, you play a song, you don't necessarily have to memorize the music, right? You just have to go to read the music when you're given the music. Okay, same deal here. You don't have to memorize the charge of an oxygen ion or of an aluminum ion or whatever. You just need to be able to read the notation when you're given it. Okay, if you see this in a question, and there's a, I don't know, decent chance that you see this notation in a question at some point. You just need to be able to figure out what the charge is from that notation. It's okay. We talked about a conductor and an insulator yesterday as well. Conductor is that material that allows the electrons on its outermost level to move easier. Read this definition again. There's one word that I don't really like here so much. You could change it a little bit to make it a little bit better. A material in which the electrons in the outermost regions of the atom are free to move. What would make this? Just change one word. You don't even have to change the entire word. Just take one word and change it a bit to make it a bit better. Okay. Of the atoms free to move, yeah, fair enough. That's not what I was thinking of, but yeah. Okay. Man, you guys are finding all these flaws with this. Neither one of those are what I meant, but fair enough. Listen, in a conductor, it doesn't mean that the electrons are free to move. It means the electrons are freer, right? Easier, freer to move, right? I mean, whatever. It's almost semantics, right? You know what we mean here, but it's not like they can just do whatever they want, right? There has to be a reason. They're freer to move. Whereas an insulator is a material in which the electrons are not I don't know if I want to say not free to move around within the substance. They're not as free to move around the substance. They'll still move, right? If I have a conductor and I have another charge and I touch that and I transfer 10 coulombs of charge to that conductor, depending upon the shape of the conductor, if it's a nice uniform sphere, then those charges will become pretty much evenly distributed around that sphere. But if I have an insulator and I touch it with 10 coulombs and transfer 10 coulombs to it, then those 10 coulombs of charge will be more concentrated near the point of contact. They're not going to evenly distribute because the charges don't move around as easily. Some of them will still go, but it won't be even because they don't move around as easily. All right, last thing. Our 3 laws of electric charge. This is where we left it off yesterday here. In any particular order here, right? I have them listed in this order, but whatever. It's not like Newton's laws where there's a certain first law and a certain second law and a certain third law. One of them, in random order, says unlike or opposite charges attract. What do we mean by that? What does the word attract mean, first of all? David? Yeah, they get pulled together, right? And what do we mean when we say opposite charges or unlike charges? Yes, and a positive will attract a negative, right? So David says a negative will attract a positive. Yes, it will. A positive will attract a negative with an blank and blank, with an equal and opposite force, right? The force on the negative will be equal and opposite to the force on the positive. Even if the charge on the negative is bigger, doesn't matter. The forces will still be equal and opposite. And it'll be an attractive force. Now, the second one that I have listed here, again, it doesn't really matter what order you've given to me in, but it says like charges repel. What does that mean? Repel. Yep. Yeah, they push each other away. Sometimes you're sitting next to somebody in class and they smell and you find them repulsive. What do you want to do when you find them repulsive? You want to get as far away from them as you can, right? That happens more in grade 7 than it happens in grade 12, but every once in a while. Repel means go away. Like charges repel each other. Sometimes we find that with people, right? Two people that are too much alike, sometimes just don't get along, and they repel each other. Like charges always repel each other. So positive will always repel positive. Negative will always repel negative with an equal and opposite force. And finally, the third law relates to neutral things. Okay? If like charges repel, unlike charges attract, what's the third one going to be? It's going to involve neutral things. Charged objects will attract neutral objects. Now you're going to learn a little bit later on why it's so important to understand that word objects is critical. I'll give you a brief example right now of when charge doesn't attract neutral, which will help you to see that the word object is important. I just won't tell you why that's the case until a little bit later on. Okay, if I have a negatively charged balloon, it will absolutely attract a neutral wall. I can rub that balloon against my hair, it becomes negative, put it against the wall, it sticks to the wall, and they attract, right? Now, by the way, they attract and they stick together. You would think the negative balloon would transfer negatives to the wall would become negative, the balloon would become negative, and then they would repel each other, right? Anybody want to take a stab at why that balloon does not transfer too much charge to the wall and they don't repel each other? Yeah. Yes, because the wall's not a conductor, right? If that wall was metal and our balloon was metallic, then we would get a lot more charge transfer, and we would find potentially that they both become negative, and the balloon would then start repelling. Okay? But regardless, the balloon will be attracted to the wall because charged objects will attract neutral objects. But a proton will not electrically attract a neutron. They do by that strong nuclear force. but not electrically. We need to have not just a neutral thing like a neutron, we need to have a neutral object like a wall or like another balloon that's neutral or something. Your hair, okay, if you have a charged comb and you bring the comb to your hair starts standing up, right? You have to have a neutral object like your neutral hair, okay, not just a neutral thing. And we'll see why in a little while, we'll see why that's the case. Make sense? Okay, one more law. We're going to call this one separate from these three. We're going to call it the law of conservation of charge. You can probably figure this one out, the law of conservation of charge. It's kind of like the law of conservation of energy or conservation of momentum or conservation of matter or conservation of X, whatever X is. The law of conservation of X says X can't be created or destroyed. Fill in X, whatever you want. The law of conservation of charge says that charge can't be created or destroyed. But just like momentum that can't be created or destroyed, you can transfer, right? When two things collide, two football players collide, one of them gains momentum, one of them loses momentum. But the total amount of momentum remains the same. Charge works the same way. You can transfer from one thing to another, but you can't create it or destroy it. When I walk across the carpeted floor in my leather-soled shoes, I gain a pretty big amount of charge, actually. And then I go to touch somebody in the finger, and I transfer a lot of that charge. Whatever charge I lost, they gained. The total amount of charge remained the same. Okay, let's do an example here. There's actually two examples that I want to do, and then that's pretty much it. If we have extra time, then I'll allow you guys to work on a practice question set that's due on Monday. Example number 2 says two charged objects, similar size, similar shape, similar material. I'll explain in a moment why that's important. Momentarily touch each other. The first object had a charge of 2, next one had a charge of -3. What's the final charge on both objects? Listen, when two things touch each other, when they have different charges, the goal is to balance those charges. That doesn't always happen. They don't always balance out. Sometimes they don't balance out because one object is a lot bigger than the other one. A big object can hold a lot more charge than a small object, right? Sometimes it's because of a shape. Okay? An object that's nice and rounded and uniformly rounded can hold more charge than something that's pointy. Okay? Certain different materials can hold different amount of charge as well. But if we have a situation where we have like pretty much at least same size, same shape, same material, then we can assume that when one object touches another, the charge will will balance out. Does that make sense? So that's what we're really saying here, is that the charge is balanced. We start off with, well, this guy is 2 times 10 to the negative 6. This guy is -3 times 10 to the negative 6. All we're going to do is add them up and divide by 2 to find out what they become. They become -5 times 10 to the minus 7. Look, what was the charge initial? -1 times 10 to the minus 6. What was the charge final? Well, each of them have 5 times 10 to the minus 7. If we add those up, it becomes -1 times 10 to the minus 6. So charge transferred, charge moved from one to the other, but the total amount of charge remained the same. Which one gained? Which one lost? How about this one? The one that was positive. Became negative, right? They both became -5 times 10 to the minus 7. The one that was positive and became negative, did it gain or lose? It gained. You can't become negative by losing electrons. This one gained electrons. Well, it must mean the other one lost electrons, but let's just double check that. This was -3. Now it's -5 times 10 to the minus 6 times 10 to the minus 7. It's still negative, but it's less negative than it was before, right? If it's less negative, it means we must have lost electrons, right? That make sense? And finally, one more. This one's a little harder, but as we work through it, you're going to find out it's not so bad. This one says ball number 1, charge of +3. Number 1 touches number 2, which is -1. 1 and 2 are separated, then 1 touches 3, which is a charge of -5. What's the final charge on all 3 of them? In this case, can we just add them up and divide by 3? Say yes or no? No, we can't. If they all touched each other at the same time, we could do that, assuming similar size, similar shape, similar material, right? But they don't touch each other at the same time. It's separate events. This happens, and then this happens. We have to treat it separately. Here's what I suggest you do for this question, and for questions like this. Make a little chart. Here's ball number 1. Here's ball number 2. Here's ball number 3. The charge on ball number 1 is +3. Ball number 2 initially is -1. Number 3 initially is -5. And the total charge, my fourth column, is going to be what? 3 plus -1 plus -5 gives me -3. I'm creating this fourth column for total charge. It's just as a little check. Every step along the way, I want to make sure that my total charge has remained -3. Yep. How to get this one? -5 for this one? This isn't the total charge. This is the charge on each one, right? So object 1 touched object 2. The total charge before they touched was -1. The total charge after they touched was -1. If I add 5 times 10 to the -7 and 5 times 10 to the -7, I get -1 times 10 to the -6. Does that make sense? So we just solve for a different thing here, right? What's squared off here is the charge on each ball, whereas the charge right here is the total charge on all 3 of them combined. Okay? Does that make sense? All right. Now, there's an event that takes place. 1 touches 2. So let's circle 1 and 2 here. 1 touches 2. Are they going to balance? Yeah, it's pretty safe to assume that they balance. So what are they going to balance out to be? 3 plus -1 is -2? Or +2, I mean. Yeah. You're going to balance it to be 2? No, they're going to balance out to be 1 and 1, right? +1 and +1. What happens to the third one? Nothing's happened. Yeah, it doesn't change. Let's add these up, see what it becomes. +1 plus 1 and -5 is -3. Okay, looks like I'm on the right track here, right? My total charge is still the same. Now it says 1 and 2 are separated. 1 now touches 3. 1 touches 3. +1 and -5. That's -4, isn't it? But they're going to balance out to be -2 on each. 1 plus -5 divided by 2 gives me -2. What about the second one? Caleb, second one just stays +1, right? It's not doing anything in this one. Let's add these up just to make sure. -2 plus 1 minus 2 gives me -3. What's the final charge on each of them? -2 plus 1 and -2. We can be, I would say, at least 95% confident we did this question correct. Could have made a mistake somewhere. It's theoretically possible. But why am I so confident that I've done this correct? Was your hand up? No. Because the total stayed the same. What are the odds of me doing it wrong and still getting the total staying the same through the whole question? It could happen, right? It could happen, but not likely. Yeah. Well, yes, that's true. Yeah, if you use the wrong initial charges, then absolutely you will get the same total charge. It'll just be wrong if you copy it down wrong in the first place. Yeah, that's a good point.